Now, actually, another thing that you know from our earlier courses, if you have studied enough, that if we have a sequence of geometric random variables, okay, so let's just say we have R different, distinct geometric random variables, but they are identical, and they all have the success probability P, okay? Imagine now you have a die, and you are tossing this die until you get a 6. And the same operation is going to be repeated by all of your friends. So let's just say x1 is the number of die tosses until you get a 6, and x2 is the number of die tosses necessary until your friend gets a 6. Okay, and every friend of you is basically repeating this experiment in parallel. Now, the total of these geometric random variables is going to be a negative binomial random variable where the success probability is P and the number of successes to observe is equal to R. Now, instead of making your friends to make this experiment, after finishing your experiment, you can restart the experiment by yourself. So instead of tossing the die until getting a 6, you can toss the die until you get a total of R6 values. And that is going to be a negative binomial random variable. In short, if we have independent and identically distributed geometric random variables, their sum is going to be a negative binomial random variable. Now, if you notice that the expected value and the variance of the geometric random variables are respectively equal to 1 over p and 1 minus p over p square. Now, I don't know if you remember it from the negative binomial distribution, but the negative binomial random variable has the expected value equal to r over p, and the variance is equal to r times 1 minus p over p square. Now, you see, because y, the negative binomial random variable, is the sum of independent and identically distributed r geometric random variables, we know that the expected value of the sum is equal to the sum of expectations. Therefore, the expected value of the negative binomial random variable would be r over p. And similarly, the variance of y, the variance of the negative random variable, will be the variance of the sum of these IID geometric random variables. And that is going to be equal to the sum of individual variances plus all dual combinations of covariances, okay? So both in the upper triangular and the lower triangular part of the covariance matrix. Now, and then we know that because these geometric random variables are independent from each other, they are independent from each other, these covariance values are going to be equal to 0, and therefore we are just going to sum up the variances of the geometric random variables, and then the negative binomial random variables variance is going to be r times 1 minus p over p square, as you can see here. Now we are going to solve a similar question as we have done in the previous day. On yesterday, we have solved a question really based on a conditional probability. And this time we are going to experience a similar question like this. In a basketball game, James is likely to score a 3-point shot with probability 0.3. So James is a basketball player, and whenever he tries a 3-point shot, he becomes successful in scoring it with 0.3 probability, but there is a chance also that he misses with 0.7 probability. We assume independence between the success of his each shot. So at every trial, the probabilities are going to be the same, and he does not lose motivation because he misses his earlier shots, or he does not gain encouragement because he succeeds in his previous shots. Okay, every trial, every shot that he tries to score, they are going to be independent from each other. So the narrator of the game tells us that James has scored his second 3 points in his 8th shot. Okay, so right now, from the beginning of the game, it has been 8 tries for the James Okay, for James, James has tried the 3-point shot for 8 times. And in his 8th shot, he has scored his first 3-point score. I'm sorry, second 3-point score. Okay, he has scored his second 3-point shot in the 8th shot. Now, the question is this. One of the previous shots is also scored, right? So in his previous 7 shots, one of them was a score, and the other remaining 6 of them was a miss. What is the probability that his first 3-point score was his third shot? So the question is asking me that. What is the probability that his first 3-point score was in his third shot? Now, again, we are going to use this analogy. Let's just say X1 is the number of shots that James need to make or need to take until his first 3-point score. After his first 3-point score, let X2 denote the number of additional shots that James needs to take until his second 3-point score. So basically, from the start of the game, we are counting the number of James 3-point shots until he scores for the first time. So we count them 1, 2, 3, so on and so forth. When he scores, we restart the process. We start from the beginning and we start counting from the beginning. Now we are counting for James to score another 3-point shot. And that count is going to be X2, the additional shots until he scores the second 3-point score. Now we know that because geometric random variable is memoryless, you know, it is memoryless, just like the exponential random variable. Geometric random variable is also memoryless. And because at his every trial, James is independently scoring these shots, X1 is a geometric random variable with success probability 0.3, and X2 is also identical to X1, but independent from that. So both X1 and X2 are geometric random variables with success probability 0.3. Now, we define the summation of X1 and X2, and that is the total number of shots that James needs to take until his second 3-point score from the beginning of the game. And we know that that is a negative binomial random variable with success probability 0.3, and the number of successes that we need to observe is equal to 2. R is equal to 2. So the narrator says that James has scored his second 3-point shot in the 8th trial. Second 3-point shot has been observed in the 8th trial. So we observe that X is equal to 8. Then the narrator asks, actually, the question asks, what is the conditional probability that we observe his second 3-point shot in the 8th shot? Given that, given that his second 3-point score is being observed in the 8th shot, what is the probability that his first 3-point score was in the 3rd shot? So basically, the question is mathematically asking me the probability of X1 to be equal to 3, given that X, or in other words, X1 plus X2 is equal to 8. Now, that is the probability that I need to answer, and we expand that probability again by writing the probability of the intersection of both the event of interest and the event of condition in the numerator, and in the denominator we write the probability of the conditioning event. And the probability of the conditioning event is the probability of X being equal to 8, and the intersection of X1 being equal to 3 and X1 plus X2 to be equal to 8 means X1 is equal to 3 and X2 is equal to 5. So that means the joint probability here can be rewritten as the product of the individual probabilities, because the trials until scoring our first shot and then trials until scoring the second shot are independent from each other. Therefore, we write that the probability of X1 to be equal to 3 times probability of X2 to be equal to 5 here, and in the denominator we have the probability of X to be equal to 8. Now, the rest is basically using the probability mass functions of the geometric random variables in the numerator And in the denominator, we use the probability mass function of the negative binomial random variable. And that is going to be for geometric random variables, p times 1 minus p to the power x minus 1. And for the negative binomial random variable, it is going to be r minus 1 choose x minus 1 times p to the power x times 1 minus p to the power r minus x. And as you can see, all of the p values here and 1 minus p values are going to be canceling out. And the result is just going to be 1 over 7. Now you see, I have not plugged in the p value at all. So James has the success probability 0.3. But instead of this 0.3, if I have told you that we do not know the probability, if I do not give you his success probability, you would be still answering this question, my friends. So P is not affecting the result. It is 1 over 7, which means if James has scored his second 3-point shot in the 8th trial, because all earlier trials are independent from each other, that first score can be any one of the first 7 trials. It can be the 3rd shot with 1 over 7 probability. It can be the 4th shot. So every earlier trials have the same chance to be scored, which is 1 over 7. Okay, if he only scored 1 3-point shot until the 7th trial, until the end of the 7th trial, then that 1 3-point shot can be any one of them with 1 over 7 probability. Okay, why is that so? Because of the memorylessness. Because geometric random variable is memoryless, we observe that situation. Okay, now we are going to talk about the sum of normal random variables. So let's just say x1 is a normal random variable with location parameter mu1, which is also the mean, and standard deviation sigma 1. And independently, I define another normal random variable x2, and it is going to have the mean of mu2 and the standard deviation of sigma 2. Now, in other words, in mathematical representation, we say that x1 is normally distributed with respective location and scale parameters mu1 and sigma 1, and x2 is also normally distributed with respective location and scale parameters mu2 and sigma 2. Now, these two random variables are independent, says the text. If we define y as the sum of x1 and x2, then y is also going to be a normal random variable with location parameter or mean mu1 plus mu2, and its standard deviation is going to be equal to the sum of the variances then taken the square. So the standard deviation of the sum of these two normal random variables will be the square of the sum of the variances. Or in other words, the variance of the y, random variable y, will be equal to the sum of the variances of x1 and x2, as you can see here. After taking the square of the sum of the variances, we get the standard deviation of y. So namely, if we have two independent normal random variables, their sum is going to be normally distributed with location parameter as the sum of respective location parameters, and with scale parameter as the square root of the sum of the respective variances. Now, of course, not every time two normal random variables are correlated, okay, independent. Sometimes they may be correlated. So let's just this time say x1 and x2 are not independent, and they introduce a correlation rho. There is a correlation between x1 and x2, and that is equal to rho. And x1 is normally distributed with location and scale parameter mu1 and sigma 1. x2 is normally distributed with location parameter mu2 and sigma 2. And the correlation between x1 and x2 is equal to rho. Now remember, correlation value can be can be between -1 and +1. It can take any value between -1 and +1. And in that case, if we sum these two correlated normal random variables, the summation is still going to be a normal random variable. Again, the location parameter will be mu1 plus mu2. Why mu1 plus mu2? Because we know that the expected value of the sum is equal to the sum of individual expectations, right? And how about the variance of the sum? Remember now, the variance of the sum is equal to the variance of the first random variable plus the variance of the second random variable, which are respectively sigma 1 square plus sigma 2 square in normal distribution, plus 2 times the covariance, right? 2 times the covariance. Now we have 2 here, and how can we calculate the covariance? By multiplying the correlation with the square root of the product of the variances, which are the standard deviations, okay? So please remember from the correlation definition, so let me show you the correlation. The correlation is equal to the covariance divided by square root of the variance of x and variance of y. Now, if you take that square root to the left-hand side as a multiplier, you can calculate the covariance of 2 random variables as their correlation multiplied with the square root of the product of the variances. Now, this is exactly what we are trying to do here. And the covariance is calculated by multiplying the correlation between these 2 random variables with the standard deviations of these normal random variables, which are respectively the square root of the variances. Now, the interior of the square root is the variance of y, and the standard deviation of y is the square root of this variance. Therefore, if you do not have any correlation between these 2 normal random variables, this is the formulation that you are supposed to use in order to calculate the standard deviation of the sum. However, if they are correlated, then you need to add this correlation term by multiplying it 2 and with the respective standard deviations. Okay? So whether the correlation is positive or negative, that may either increase the standard deviation or reduce it. Okay? It may also, if the correlation is negative, it is possible that this may also be reduced, okay? The standard deviation can be even lower than it's supposed to be in the independent case. So it depends on the sign of the correlation. Now we are going to solve a question related to that, and maybe another one later, so we'll see about it. In this question 13, it says, let X denote the amount of rainfall to Istanbul in millimeters on a randomly selected day of the year, and let Y denote the same for Trabzon on the same day. Now, X and Y are the rainfall amounts on a random day in Istanbul and Trabzon, okay? But on the same random day. That random day is selected, and we are measuring the rainfall amounts in both cities on the same day. Do you think that are they going to be correlated or not? Now, they are going to be correlated. Why? Because they are on the same latitude, right? Trabzon and Istanbul, these 2 cities are staying on the same latitude, and they are both cities which have coast to Black Sea, as you know, okay? And therefore, if you observe a rain in Istanbul, it is most probably that you also observe a rain in Trabzon as well. Or, for example, if it is not raining today in Trabzon, then most probably you will not observe any rain in Istanbul as well. Okay, so it is possible that we may have a certain correlation between the rain amounts in these 2 cities. Now, X is normally distributed, the rainfall in Istanbul is normally distributed with 1.2 millimeters mean, and the variance is equal to 0.09 millimeters square. And the rainfall in Trabzon is normally distributed with a mean of 1.6 millimeters and variance of 0.04. Now you see the expected amount of rainfall in Istanbul is less than the expected amount of rainfall in Trabzon. I mean, that is actually pretty normal. I mean, we know that we experience rain in Trabzon much more than we experience it in Istanbul. However, the variance of the rain in Istanbul is a lot larger than the variance observed in Trabzon, because it's a common thing that we observe rain in Trabzon. Okay, therefore, there is not a variance in the situation. But as we can see days with no rain in Istanbul, we can also see rainy, very heavy rainy days. Therefore, the variance in Istanbul can be greater than the variance in Trabzon. Now, we also have the correlation measure between X and Y. So the rainfall amounts between Istanbul and Trabzon on a random day of the year, also they have a correlation, which is 0.4. So there's a positive correlation here, as we have expected. What is the probability that the total amount of rainfall to Istanbul and Trabzon on any day to be greater than 3.5 millimeters, it says. So the question provides me this information. X is normally distributed with location parameter 1.2 and scale parameter 0.3, and Y is normally distributed with location parameter 1.6 and scale parameter 0.2. How do we understand the scale parameters are equal to these values? Now, be careful, the question gives me the variances, not the scale parameters or standard deviation. So you need to take the square root of the variances here to calculate the scale parameters as 0.3 and 0.2. And then the question asks me the probability. What is the probability of the total amount of rainfall in Istanbul and Trabzon, which is X plus Y, to be more than 3.5 millimeters? Now, one thing you need to be careful here, there is also a correlation between X and Y as 0.4. Now, according to the descriptions we have given in the earlier pages, the sum of two normal random variables, whether they are independent or correlated, is also going to be normal. And the location parameter of the sum is going to be equal to the sum of the independent location, sum of the individual location parameters, which is going to be 2.8. As you can see, 1.2 and 1.6 is 2.8. And the standard deviation of the sum is going to be calculated as the square root of the variance of the first random variable plus the variance of the second random variable plus 2 times the covariance between these two random variables. And the variances are respectively 0.09 and 0.04. And the covariance is calculated by multiplying the correlation with the respective standard deviations. And that result is going to be the square root of 0.178, which is 0.422. Now, the question basically gives me that information. The total amount of rainfall in Istanbul and Trabzon on the same day is going to be normally distributed with location parameter 2.8 and scale parameter 0.422. And the requested probability is what? The probability of the sum of these two random variables to be greater than or equal to 3.5. Now, how do I solve such a probability related to normal distribution? What is the golden rule? I don't know if you have done this in the exam or not. The golden rule is the probability of this probability statement should be standardized, right? So we need to subtract the location parameter from both sides and divide the difference to the scale parameter. And the left-hand side will become a standard normal random variable, and the right-hand side will be equal to 1.659. And the probability of Z being greater than 1.659 is what? 1 minus the CDF, standard normal CDF, at the same value. And at 1.659, we can check the CDF of the normal distribution from the table and subtract it from 1, and the result would be 0.0486. So the probability that the total amount of rainfall in Istanbul and Trabzon on a random day of the year to be more than 3.5 millimeters is equal to 0.0486. My friends, of course, these values are made up values, okay? I mean, I do not really know the expected amount of rainfall in Istanbul and Trabzon at all. These are just made up values. I mean, if you intend to check the meteorology sites, you are going to totally see different values than this, okay? Now, let's solve another question. And this question is a little different than the previous question. So this time we have X and Y, which are two normal random variables. X is equal to what? X is normally distributed with location parameter 10 and scale parameter 2. and y is normally distributed with location parameter 15 and scale parameter 3. And there is also a correlation between these two random variables that is minus 0.5. Now the question asks me a probability statement related to not the sum of these two random variables. In fact, it asks me the probability of 3x minus 2y. So this is not a summation. This is a difference. Also, we are multiplying these values with constant values, with coefficients. Now, what is the probability of this to be less than or equal to 10? The question asks. Now, actually, you may think that this is not a sum, so we may not be able to solve that. Actually, this is a summation, my friends. Now, you know, the linear transformation of normal random variables are also normally distributed, right? So in the chapter where we have explained the normal distribution, we have given this proposition: if x is a normal random variable, then if you multiply that normal random variable or add and subtract another normal random variable from that, it does not matter. The result is just going to be a normal random variable again. Why? Because this is a linear function. Linear transformations of normal random variables are always normally distributed. So we know that 3x minus 2y, it is both linear transformations of x and y, and it is also a summation operation. So subtraction is a kind of summation, if you remember from yesterday's course. Therefore, 3x minus 2y is also going to be a normally distributed random variable. All we need to do is to determine the location parameter and the scale parameter for 3x minus 2y. So for that, I am going to determine the expected value of 3x minus 2y first, because the expected value of 3x minus 2y will be equal to its mean, its location parameter, right? And that expectation is equal to 3 times the expected value of x minus 2 times the expected value of y. And since expected value of x is equal to 10 and the expected value of y is equal to 15, the result is going to be 0, which means 3x minus 2y is basically a normal random variable with location parameter 0. Now I would like to determine its scale parameter. So in order to determine the scale parameter, I need to calculate the variance of 3x minus 2y first. The square root of the variance is going to be equal to the standard deviation, which is going to be called the scale parameter. Now, variance of 3x minus 2y is equal to variance of 3x plus variance of minus 2y plus 2 times the covariance between the first term and the second term, 3x and minus 2y. If you remember from yesterday's course, 3 can get out of the variance by squaring it, minus 2 can get out of the variance by squaring it, but these 3 and minus 2, given as coefficients inside the covariance, they can get out of the covariance without any change, and therefore the result is going to be 9 times the variance of x. What is the variance of x? It is the square of the standard deviation, right? So it is going to be 4. So 2 squared, 4. Plus we have 4 times the variance of y, and the variance of y is going to be 9, minus 12 times the covariance between x and y. Now we do not know the covariance of x and y. What we know is the correlation between x and y, but if you remember, the covariance of x and y will be equal to the correlation of x and y times the square root of the variance of x and variance of y. The correlation of x and y is minus 0.5, and the square root of the variances are equal to the standard deviations, which are respectively equal to 2 and 3. Therefore, the covariance is equal to minus 0.5 times 2 times 3, which is minus 3. When I plug in this minus 3 value in place of this covariance, the result that you are going to get in the end is 108, which means the variance of 3x minus 2y is equal to 108, and the standard deviation is going to be equal to the square root of this variance. Therefore, 3x minus 2y is also going to be a normal random variable with location parameter 0 and scale parameter square root of 108. The desired probability here is a normal probability statement for the sum 3x minus 2y to be less than or equal to 10. So what we are going to do is the standardization once again. We subtract the location parameter from the both sides and divide the difference to the scale parameter. So the left-hand side is going to be a standard normal random variable, while the right-hand side is going to be equal to 0.962. And the cumulative probability of normal random variable at 0.962 is approximately equal to 0.8320 according to the CDF table of the standard normal distribution. Now, we can generalize these statements about the sum of two normal random variables to more than two normal random variables. Actually, my friends, this is an important part of this topic because we are going to use that in the next chapter. More generally, if we have a sequence of normal random variables with respective means mu I and standard deviation sigma I, so we have a sequence of normal random variables. Let's just say the ith member of the sequence xi is normally distributed with location parameter mu I and scale parameter sigma I, and this definition is given for all random variables in the sequence. And further, suppose that each couple in this random variable sequence has a certain correlation. So the ith member of the sequence is correlated with the jth member with a correlation of rho ij. And in that case, if we define y as the sum of these normal random variables, then the location parameter of this sum is going to be equal to the sum of individual location parameters, summation of mu1 to mu n, and the standard deviation will be equal to the square root of the sum of the individual variances plus 2 times the correlation between each couple of random variable and their standard deviations multiplied. However, I is changing from 1 to n minus 1 and j is taking greater values than I. So because we are multiplying the upper triangular elements of the covariance matrix here with 2, we are not summing over the lower triangular elements, just like we have done in yesterday's course. Okay, so for all possible dual combinations within this sequence, such that the index I is less than the index j, you multiply the correlations with the respective standard deviations, and you also multiply them with 2 because you do not consider the indices where I is less than, greater than j. Okay, you know that the covariances are symmetric, therefore we do not need to multiply them again when the random variables are swapped. Instead, we multiply these covariances with 2 simply. So this is the end of chapter 8, my friends. Please do your reading assignments again.